and welcome to it, our grade 11 prep answer presentation. Okay, question 1 as per usual would start with solving certain equations. Over here we just need to follow the zero product rule once again. Okay, to go from left to right we can see descending powers of x, so that is our standard form, which of course includes everything being equal to 0. The factors we are looking for over here is x minus 5 and x minus 3. Applying that zero product rule once again, that's a times b being equal to 0. That's if and only if a is equal to 0 or b is equal to 0, which means that's how a, so x minus 5 needs to be equal to 0, and that's how b, again, or x minus 3 needs to be equal to 0. Firstly, x is equal to 5 or x is equal to 3. It's as good as that gets. For some mark allocation, well, factorization gives you a mark, and then a mark for each answer. Moving right along. Well, this phrase means don't even bother trying to factorize. Run straight to the much wanted quadratic formula, which states the following: x is equal to minus b plus minus the square root of b squared minus 4ac, or divided by 2a, which is then ripe for substitution. So everywhere we see a letter, well, we just substitute for a set of brackets. So that's b squared minus 4ac, everything over 2 times a, of course. Let's pick another color to do the actual substitution. So our b value is -5 over there, so that goes there and there. That's our a value, that goes there and there, and then remember, with the sign included, it's -1. All of this only works if everything is equal to 0, and our standard form is once again present. Remember, this is still a quadratic equation. Well, once we resolve that just using our calculator, we should have that x is equal to 1,85 or x is equal to -0,18. As you can see, 2 decimal places. Well, substitution gets you some marks, and your final answer should get you some marks as well. It could be boiled down to 4 or 3 marks, depending on how generous your marker is. Well, now we have inequality of the quadratic nature. Well, that's what we've been dealing with. So let's just take this and swap those terms around. So we'll have -2x squared plus 4x. Remember, I like descending powers of x. And then let's just divide by -2. Okay, so we're going to divide the entire inequality by -2, which means we'll have x squared minus 2x. We'll have a 0, but because we divided by a negative, the inequality will flip. It becomes greater than instead of having been less than. From here we can still factorize. Yeah, I'm trying to factorize, so we can only take out 1x, so that will be x multiplied by x minus 2 in brackets greater than 0. So now we are ready to address our critical values. That is, of course, where this function will cross the x-axis. Remember, above will be greater than and below will be less than. We are looking for these values. These are the critical values. As we can see over here, those critical values would be x being equal to 0 and x being equal to 2. So smallest value on the left 0 and largest value on the right. Now we can address this. Well, we are looking at the area above the x-axis, which means it's this arm and this arm, and we have a look at where they throw a shadow on the x-axis, which means the solution is split, because this is where we find it, where x is less than 0 or where x is obviously greater than 2. And we still need to see how the marks get split. Well, factoring from standard form, we have critical values, and then obviously our answers. 1 or 2 marks, that will do for that. Okay, over here we have exponents. So if we have a look at this term, which is 2 to the power 3x, we can split it and have it say 2 to the power 3x and then 2 to the power 1 plus 2 to the power 3x, all equal to 12. So let us address this part. Well, a to the power m multiplied by a to the power n is equal to a to the power m plus n. And if we have a look at this, that is the application of the law, but all we've done is applied it in the right to left direction, or in reverse, because this will turn into that if I move backwards. So what was the point? Well, the point was to create a common factor, which I can then take out. That's 2 to the power 3x. What's left in this term is a 2, and what's left over there is plus 1. So there, I've properly factorized it, and that is equal to 12. Well, 2 plus 1 is just 3. Now I can divide both sides by 3, which, well, anything divided by itself is just equal to 1. So 2 to the power 3x is equal to nothing else then other than 4. And 4 can be rewritten as 2 to the power 2, which means I can now equate exponents, and I'll have 3x being equal to 2. Thusly, x is equal to 2 over 3. It's good. Well, if we have a look at how marks might be distributed, creating a common factor over there, and then the simplification as well as the final answer should get you more than enough for those 4 marks, or maybe just adequately enough. Well, again, white might not be the best color for this. Let's go. Well, over here we have an equation that includes a surd. Well, obviously we'd like the surd to be alone. Pay attention to the fact that it's the principal root. Right? So first things first, let's subtract 2 from both sides. That zeroes out, and we are left with the square root of x minus 1, and then x negative 5 minus 2 is equal to minus 7. So that's good. Now we can square both sides. So the point was to do this. If we have a look at it, squaring that side and squaring that side, so this becomes x squared minus 14x plus 49. And then if we simplify even further, we'll have x squared. I'll subtract x from both sides. That was the point over here. This becomes minus 15x, and then obviously add 1 to both sides. That becomes 0, and this becomes 50. Well, factorization is quite simple, so that will be x minus 5, x minus 10. Again, feel free to use your quadratic formula. You are well within your rights. But over here we can see that x is equal to 5 or x is equal to 10. Now, you are not done. anytime there is a third involved, because it's the principal root, the positive root, that's why I marked this, it requires some testing. Well, if we have a look at this, that says 5, so 5 minus 1 is equal to 4. Square root of 4 is equal to 2. And then over here we shall have 5 minus 7, which is minus 2, which means that this value becomes invalid. And then if we have a look at 10, 10 minus 1, for 10 we have the value 3 as a result if we test it, and 10 minus 7 gives us 3, so that one is good. So that's completely good. So let's have a look at how marks might be allocated. Well, for squaring both sides, getting to standard form, factoring your answers, need to cheat and have a look over here. And then for testing, although I may or may not have been overly generous, or in this case maybe stingy, however, moving right along. And now we have some simultaneous equations. Always our first step will be to label after rewriting. Let's see what I mean by that. So that's equal to 0, and we apply the label 1. And then for this equation we have y being equal to minus x squared plus 2x plus 8. That's obviously going to get labeled as number 2. So let's get cracking. So from the first equation, what we'll do is we'll add y to both sides, and then as we can see, we will end up with y being equal to 3x plus 2. We can label that as equation number 3, and as per usual, just substitute equation 3 into equation 2. In this case, you can also set equation 2 equal to 3 because the left hand sides are equal, which means the right hand sides must also be equal. However, what we'll have is 3x plus 2 being equal to minus x squared plus 2x plus 8. Well, let's transpose everything over to the left. So we'll add x squared to both sides, that's zeros out, so we'll have x squared, then we'll subtract 2x from both sides, that's zeros out, which will give us plus x, and then we subtract 6 from both sides, no, we subtract 8. I think my brain was jumping the gun because we have minus 6 when we're done, and that's obviously all equal to 0, as we can see, because everything has zeroed out. So what happens now is just plain and simple factorization. So that will be x plus 3 and x minus 2 all equal to 0. Therefore x is equal to negative 3 or x is equal to 2. Let's not forget that we still have a y to solve for, so if we sub minus 3 in here, we'll have minus 9 plus 2, which would be equal to negative 7. And then if we use the 2, 3 times 2, which is 6, and 6 plus 2 is equal to 8. which is boring, but okay, let's go. Show that the roots of 3x squared plus k plus 2 in brackets x times x is equal to 1 minus k. We want those roots to be real for all values of k. So first things first, again we're still dealing with quadratic stuff, so standard form is still a thing, which means we will have 3x squared plus, well, leave that k plus 2 as the coefficient of x, and then we'll transpose this. So we'll have plus k on both sides, and then minus 1. And that's all equal to 0. So let's have a look at our values. So that's a, and then for b we'll have that, and that will be c. So let's get ready. Well, given this is nature of the roots, or as I like to call it, what kind of number is x? Which means we are looking at our discriminant denoted by capital delta, Greek delta for that matter, which comes from our formula, which is b squared minus 4ac, the bit under the radical sign. And in this case we have b, which is just k plus 2 all squared minus 4, value of a is obviously 3, and the value of c is none other than k minus 1. Well, if we simplify this, we'll have k squared plus 4k plus 4, that becomes minus 12, so we'll have minus 12k, and then if I have a look at it, plus 12. Simplify this even further, so we'll have k squared, that becomes minus 8k, and that is plus 16. And through the magic of factorization, we'll see that this is k minus 4 all squared. So regardless of what value you put into k, what real value you put into k, this number is going to end up squared. Therefore k will always be an element of real values, okay, because k minus 4 all squared is always going to be greater than 0. So whatever number is in here, whatever real value is in here, that real value is going to get squared, so it's going to always be greater than and equal to 0, which is all you need for all roots to be real. Okay, yes, I do owe you mark allocation for that one, which will come in the form of substituting correctly into delta or the discriminant, making sure that we simplify correctly, getting delta as a perfect square over there, and then making sure that our conclusion is written in a way that is logical. Right, now time to do some simplification, because expressions need not be so complex or complicated. So first things first, well, let's just apply our laws as we see first. So over here we can see that is a power of 2 and that is a power of 2, so we'll leave the 2 alone. We'll just have 2 to the power x plus 2, and then 4 is 2 squared, and then the original x plus 1 exponent remains. At the bottom we'll have 2 cubed, and by the same token the original exponent remains. So 2 to the power x plus 2 stays as is, and then we just need to distribute over here, because the power law, where power is raised to a higher power, we just multiply that. So let's apply it properly. 2 times x is 2x, and 2 times 1 is 2. At the bottom, by the same token, we'll have 3 times x is 3x, and 3 times negative 1 is just negative 3. And now we can apply law 1 and 2 simultaneously. So in the numerator, we are multiplying, which means we'll just add up the exponent. X plus 2x is equal to 3x, and 2 plus 2 is 4. So that takes care of that. Then we'll subtract, open up a bracket, and we have 3x and minus 3. So if we use another color, we can see that 3x and minus 3x, that will zero out when we multiply that in, and then we'll have 4 minus minus 3, which is just 2 to the power 7. And well, even without the calculator, that is still 128 all day long. And as far as mark distribution goes, what we'll do is, well, correct application of your exponent laws will give you 2 marks, and then your final answer is the final mark. Ooh, we skipped there. Apologies for that. Well, same principle in terms of applying exponent laws, but always careful, because now we are subtracting them from each other, which means we need to know them backwards now. Why would that be? Well, let's just have a look. So we have 3 to the power x and 3 to the power 1 minus 3 to the power x multiplied by 3 to the power minus 1, all divided by 2 times 3 to the power x. Well, the idea here is because we have 2 separate terms, we need to grade one term. And for that, our main tool is always factorization. So let's just take that 3 to the power x out as a common factor. What's left is 3 minus, well, that just becomes 1 over 3. Remember, a to the power minus 1 is 1 over a. It's in our definitions. Well, back to this. It's 2 times 3 to the power x. Wow, anything divided by itself is still 1. Well, 3 can be converted to 9 over 3, and then it's minus 1 over 3 over 2. So that's 8 over 3. Well, this is divided, so divided by 2, which is equal to 8 over 3 times 1 over 2. That's just 8 over 6, which is equal to 4 over 3. So without being too pedantic, all of that counts as one thing in terms of simplification. So that's a mark. Application of the laws and those cancellations are a mark, and that's a mark. Might be slightly different depending on teacher to teacher or examiner to examiner. Apologies. If I'm erring in terms of mark allocation over here, it's probably on the stingy side. Some thirds. Well, this should be fun. Hopefully. Well, what we have here is a third multiplied by another third, and if we apply those laws, we can, because the indexes are both the same in this case too. If you don't see an index there, the index is 2. So that means, because they're being multiplied, we can rewrite them as 1/3. Now, I'm going to take this and put it in a bracket, and that and put it in a bracket. So what we'll have is x plus the square root of 2x minus 1, close the bracket, open another one, and x minus the square root of 2x minus 1. Well, why would we want to do that? Well, if we have a look at this, if we call this and this by another name, let's say that's a and that's b, then we have this form: a plus b, a minus b, obviously in the second one. Let's bracket those, and we know that just simplifies to a squared minus b squared when we FOIL them out. So we'll take advantage of that pattern, because all we need to do is multiply the 2 first terms, multiply the 2 second terms, and be secure in the knowledge that the middle terms 2 cancel out. So what will we be left with? Well, let's put in an extra step over here. So x times x is going to give us x squared, and then we'll have minus, of course, well, square root of 2x minus 1, but don't forget that'll be all squared. So that simplifies into, well, x squared minus 2x plus 1, and that simplifies to x minus 1 all squared if we do our factorization correctly over here, which is none other than x minus 1. Because remember, that's an index of 2, and the square root of a square is nothing but the base. Well, how do we allocate marks for this one? I would say, well, applying the third rule correctly over there, our simplifications, 2 marks for these steps, and then for your final answer you get that. Hopefully that's clear enough. Moving right along, for which values, or for what values of x will p be a real number? Now p can only be real if this part is real, and that part can only be real if it's positive, which will depend on that denominator. That denominator better stay positive, which means x plus 2 needs to be greater than 0. It can't equal 0 because we're not allowed to divide by 0 either, which means x needs to be greater than negative 2. As long as it stays greater than negative 2, this fraction will remain positive, and we are not worried about that value over there, because this is about being real. Somehow that sounded funky. Well, 2 marks, 1 for the correct inequality and for simplification. Show that p is rational if x is equal to 3. Well, that's straightforward substitution. So square root of 5 over 3 plus 2 is equal to, of course that was being substituted, plus 3 plus 2. So substitute my x's in the correct place, so that's just the square root of 5 divided by 5 plus, well, I made a mistake here, that's supposed to say 3 divided by 3 plus 3 over 3, which is 1. That's also 1, which is 2. Well, 2 is an element of rational numbers, and that's as good as that gets. Again, 1 for substitution and 2 for your final answer. Calculate the sum of the digits of this rather big and bombastic number over here. So let's have a look. Well, that looks kind of cool. If I remember that 2 times 5 is equal to 10, that would be sort of a clue in the basis. So I didn't pull this out of thin air, and I need a 1 over there if I want to call that number 10 on the right hand side. So what can I do to sort of take advantage of this? Because why would this be useful? Well, if you can think about it, 10 to the power 3, 10 to the power 8, and 10 to the power 1099. These numbers all have one thing in common. The sum of their digits is all equal to 1, because it's just a 1 with a bunch of zeros. A 1 and then you're adding 0. A 1 and then you're adding a bunch of zeros. So that's kind of useful if we have a look at this. So 2 to the power 2015 times 5 to the power 2019 can be rewritten as 2 to the power 2015 multiplied by 5 to the power 2015 multiplied by 5 to the power 4, because 2015 plus 4 gives us back 2019. Okay, again reverse of exponent law 1, which states the following: a to the power m plus a to the power n is a to the power m plus n. Again, reverse application. Well, now I've done a thing, because this can be rewritten as 2 times 5 to the power 2015, and that one over there, 5 to the power 4, I'll leave alone for now because I want to get to this. This is just 10 to the power 2015 because I'm allowed to multiply inside the bracket. Again, I have just reversed one of my exponent laws, and 5 to the power 4, whether you do it by hand, nothing in the sum said without the use of a calculator, so that's just 625, although it might say that on certain question papers. So that, regardless, if we follow this logic, is equal to 1 plus, so therefore we'll have 1 plus 6 plus 2 plus 5, and if we have a look at that, that's just 8, or 7 plus 7, which is equal to 14. The sum of the digits of that rather large number happens to be 14, because we have 2015 zeros involved. Mark allocation, well, simplification, maybe I'll do it in another color so it's clearer. So your simplifications and then your actual calculation for the digits. That was fun. So let's have a look at question 3. Some patterns over here. So sticks are arranged in a sequence of patterns. Here is a graphic to show how the arrangement works. So you can see we'll have 2 sticks and then all of a sudden 7. So there's some stacking going on over here, and then we have 15. Well, what do we do with that? Well, if I have a look at the questions over here, and we'll see we'll need to investigate this pattern over here. So 7 minus 2 gives us 5, 15 minus 7 gives us 8, and that gives us 3. So this must be none other than a quadratic formula, which means 15 plus 11 will have 26 over there. So write down the number of sticks needed to build pattern 4 if the patterns are continued. And as we can see over here, that needs to be 26 sticks needed to build that. Well, from our little diagram that we built over there, we can now go ahead and do the actual calculations for the nth pattern over here, for the nth pattern. So 2a is equal to 3, therefore a is equal to 3 over 2, and then using that 5, we can say 3a plus b is equal to 5, some substitution. And from that we can understand that b is equal to 1 over 2, and then our first term in the actual pattern is equal to 2, but we know that comes from a plus b plus c being equal to 2, given that it's our first term, and that'll be 3 over 2 plus 1 over 2 plus c equal to 2. All of that's equal to 2, and 2 minus 2 is equal to 0. Therefore, answer the actual question, the nth term is equal to 3 over 2 n squared plus 1 over 2 multiplied by n. That is good enough for that. Mark allocation pretty straightforward over here. You're just going to get a mark there, mark for A, mark for B, mark for C, and an actual mark for the general term as asked. Moving right along. So C, how many sticks would you need to build pattern 11? Well, that question is just asking for the value of term 11, which is equal to 3 over 2, substitute 11, and then square it, plus 1 over 2 multiplied by 11. Well, any calculator should be able to handle that and give you 176 with a very simple mark allocation, mark for substitution, and a mark for your actual answer. The final question in this set, number D, calculate the maximum value of n if you have only 126 sticks to build the biggest pattern with. Video. So let's have a look. For this, we know that Dn needs to be less than or equal to 126 because we have the 126, so it can equal 126 for that maximum value to be true. But of course, we do have a definition for Tn, which is 3 over 2 n squared plus 1 over 2n. Of course, that's our inequality. Well, then let's just multiply everything by 2 because we want to get rid of these fractions. That becomes 252, but we need it in standard form, so this becomes 3n squared plus n, remember the 2's cancel, and then that's minus 252 less than or equal to 0. Now, given that I have a prepared memo over here, took me a while, but these were the factors. However, feel free to use the quadratic formula. So see, no arrogance. I am willing to admit that it took me some time to get to these factors. Now, this is a quadratic inequality, which means we can deal with our critical values and have a look at what's happening. Well, this inequality is going to be true in terms of its critical values, where n is equal to negative 28 over 3, or where n is equal to 9. Therefore, our max value is going to be n equal to 9, because n cannot be some sort of negative number. N cannot take on a negative value. So 9 is good. 9 is going to give us 126 sticks exactly. Here we go. So given the pattern, the number pattern, 1 over 2, 2 over 3, 3 over 4, 4 over 5, y should be equal to 5 over 6, because we can see the numerators as just plus 1, plus 1, plus 1, plus 1, plus 1, plus 1, and then the same thing is happening at the bottom, plus 1, plus 1, plus 1, plus 1. And to get from top to bottom is plus 1, and that sort of answers the second question, which is quite simply Tn is equal to whatever n is, the numerator is n plus 1. I think 3 marks is a bit generous for this one. I would have been more stingy. However, we are moving right along. In this diagram, we have P being equal to negative 8 for the x value, and y coordinate is equal to t. So that's a point in the Cartesian plane such that OP is equal to 17, and we have our reflex angle XOP being given the value theta. Remember, for reference purposes, we do that from here. Ta-da! Moving right along. Okay, as previously stated, just think of an altitude being dropped down. That's an x value, so that -8 we imagine to be there, and t we imagine to be there. Then of course, according to Pythagoras, t squared will be equal to 17 squared minus -8 all squared. Let's quote our dearly departed Greek Pythagoras. That should be all fine. So t can be equal to plus or minus 15 if I complete it, and then because this is in the third quadrant and it's beneath the x-axis, the value we choose is minus 15. Okay, so this value should always speak to your diagram. There we go. T is equal to -15. That's the calculation. Now, determine the value of the following without the use of a calculator. Yes, of course, we were waiting for that. So, cosine of -theta is equal to cosine of theta. According to our reduction formulae, that is completely legal. Make a better is equal to sine over there, and if we just read this diagram properly, like I said previously, we reference from there. Cosine is adjacent over hypotenuse, so this will just turn into -8 over 17. No fuss, no muss. Yeah, that should be 2 marks. And then the second one under B, 1 minus sine of theta ends up being 1 minus 15 over 17, because opposite over adjacent, hypotenuse I should be saying. My apologies, dear viewers. Well, that if I want to do this properly without a calculator, I'll have 17 over 17, because that's just 1, and I chose 17 because of this denominator. Negative and a negative gives us a positive. That'll be 15 over 17, with the final answer of 32 over 17. Well, this step particularly over here just sort of rubs it in that you know how to work without a calculator, if I should say so myself. And in this case, I should say 2 marks is on the stingy point, whereas previously I had agreed with it being generous. It all balances out in the end. Now, if sine of 17 is equal to the value a, without using a calculator, express the following in terms of a. So first things first, let's get a little sketch going so we see what we're dealing with. So a can be rewritten as a over 1, and if we have a look at a triangle, place that in a right angle triangle, well, this will be our 17 degrees. So sine is opposite over hypotenuse, and with a little Pythagorean magic, that will be 1 minus a squared. So now if we look at a, tan of 17 is just going to be opposite over adjacent. So tan of 17 degrees is going to be equal to a divided by the square root of 1 minus a squared. If we look at b, well, sine of 107 degrees looks strange. However, sine of 90 plus 17 degrees, well, doesn't change the value of 107, just breaks it up. But this is now a bit more useful because it's a cofunction. If I remember anything about cofunctions, sine of 90 degrees plus theta. The co-function of that is cosine of theta, and that's what we'll do here with 17 degrees, taking the value of theta in this case. And if we have a look at our triangle, cosine of 17 degrees is adjacent of hypotenuse, which ends up being the square root of 1 minus a all squared over there. For C, we have cosine squared of 253 degrees plus sine squared of 557 degrees, which is equal to nothing else then, or none other than cosine squared of 180 degrees plus 73 degrees plus sine squared of 360 degrees plus 197 degrees. Well, all of this is pretty helpful, so let's see if we can just follow a bit of logic so we can create more space. Well, that just becomes cosine squared of 73 degrees. Now some of you might complain that, but sir, you didn't check the cast diagram. Well, it's being squared, doesn't matter if it's positive or negative. That's the beauty of that, because if you square positives you get a positive, if you square negatives you still get a positive. Well, over here what we'll end up with is that's a rotation, so it doesn't matter where your radius is. If you rotate it by 360 in either direction, you end up back in the same place, and that's the algebra for that. So that's just 197, which I can break up into 180 degrees plus 17 degrees, and if we do that one, we get sine squared of 17 degrees. Now this is interesting. 17 plus 73 is 90, which means it sits right over there, and I can read cosine off of this diagram, which means I'm going to have a over 1 all squared, and that's plus, well, sine of 17, whether I take it from there or from the diagram, is also a over 1 all squared, and then, well, a squared plus a squared is equal to 2a squared. There we go. Some efficiency and taking advantage of seeing what the diagram is. Of course, understanding your co-functions is also allowed over there. That gives you 2 marks. That gives you 2 marks. And then all of these, your mark distribution might vary, but I think 4 marks is pretty fair in that case. Right, 4.3, simplify fully without the use of a calculator. Let's get going on that one. So we'll have cosine of, how do we treat this? Well, we'll have minus 225 degrees. We can add a rotation if we so choose, because it just ends up back in the same place. And then we'll have sine of 180 degrees minus 45 degrees plus sine of, well, that's 360 minus 30 degrees, and that's all being divided by tan of 180 degrees plus 45 degrees. So this becomes 135 degrees, which means we have cosine of 180 degrees minus 45 degrees over here. Well, that's ready for reduction. That's just sine of 45 plus, well, this is the 4th quadrant, which means I can get rid of that, change the sign, because sine is negative in the 4th quadrant, and we'll have sine of 30 degrees. forgot to close this bracket over there. But that's the third quadrant where tan is positive, which means that's just tan of 45 degrees. Well, this becomes negative cosine of 45 degrees because cosine is negative in the second quadrant, and these are from our special triangles, which look as such because 45 seems to be the popular one in that expression. We have 1 square root 2, and then for 30-degree angles we have, well, obviously 30, that's 1, 2, 3, but the root there of. Well, for cosine of 45, of course that's negative. We are going to have minus 1 over square root 2, and that's obviously multiplied by sine of 45, which is also 1 over square root 2 minus sine of 30, which is 1 over 2. That's all divided by tan of 45, which is 1 over 1, which is just 1. Well, if we multiply these two together, we get minus 1 over 2 because the square roots will equal the radicand. That's the value under the radical. That's 1 over 2. And that's all being divided by 1, so it stays as is. Just for funsies, we'll put that there. And a half and a half is 1, but this is negative half and negative half, which gives us negative 1. I don't see that being more fully simplified, if I were to be honest. Well, I think this thing had something like 6 marks in it. So just that cosine reduction is worth 2 marks. Over there, special angles with simplification, 1, 2, 3, 4, 5, 6. Well, that goes towards that final answer. Let me group it together. Now we're being asked to prove an identity. Well, generally speaking, going from left to right is probably, it ends up being the more applied direction from left to right. However, being careful is actually a thing. So let's just rewrite our left hand side. So that says cosine x minus 1, and then we have cosine x plus 1. Now again, this pattern is there, that a plus b, a minus b pattern, which means we can just multiply the first terms per bracket with the second term partners. So what will that be? That will be 1 over cosine squared x minus 1. Now if we have a look here on top, in terms of what we need, taking out the negative 1 at the bottom, it's going to be advantageous. So we'll end up with minus 1, and that gives us the right to switch this. Well, why do I want to do that? Well, my Pythagorean identity says that sine squared x plus cosine squared x is equal to 1. And then of course, if I transpose that, cosine over, I have 1 minus cosine squared of x. So therefore, sine squared x is going to be equal to 1 minus cosine squared x. So that'll explain what I'm doing here. I'll have minus 1, and then I'll have a sine squared x. So how does that help me? Well, anything multiplied by 1 retains its own value. And the thing is, in order to get a tan squared of x, I need to divide this by cosine squared x. Then means I must multiply it by cosine squared x as well. So if we have a look at this, I'm multiplying the entire thing by 1, which means I end up with minus 1 as I need on top, and then sine squared divided by cosine squared gives me tan squared x. Oh, and wouldn't you know it, I need that cosine squared x in the denominator, because that makes it look like the right hand side. And that is proof if I ever saw it. Well, as for the mark allocation on the task, think 6 might be a bit generous. 5 is probably a bit more realistic. However, I don't think generosity is a sin. Determine the general solution for 2 sine x cosine x being equal to cosine x. Let's have a look at that. Now we have this 2 sine x cosine x being equal to cosine of x. Well, I don't want to divide by cosine of x because it's part of the thing. What else can I do? Well, factorization does exist in more than just pure algebra. We'll give this equation an algebraic treatment, as it were. So, what do I mean by that? Well, I am going to factorize a cosine x out of that expression on the left, which will leave me with 2 sine x minus 1 as my second factor over there. And now I can just apply my zero product rule, which states that a times b equal to 0, then either a is equal to 0, which is cosine x, or b is equal to 0, which is 2 sine of x minus 1 being equal to 0. Therefore, sine of x is equal to 1 over 2. Now, for our first equation, let's have a look at that. Well, where is cosine x equal to 0? Well, for this, graphical interpretation is most useful. So that value over there is 90 and that value over there is 270. Therefore, we can jump straight to the actual solution or general solution, which is going to state that x is equal to 90 degrees. Well, the phase difference, or the difference from there to there, is going to be 180, and that's going to happen every 180 degrees plus 180 degrees multiplied by k, where k is an element of integer values. Rightio. Otherwise, you'd have to say, or not both of these solutions. The other option would be to say that x is equal to 90 degrees plus 360 degrees k, but then you'd have to acknowledge the 270 degrees as well, or x being equal to 270 degrees plus 360 degrees k, and then we'd have to state x equal to 90 degrees as a reference angle first. So you have the blue option or you have the green option. Now, how about this? Well, I think this can be handled by our special triangle, although nothing's stopping us from using a calculator either. So our reference angle over here would have x being equal to 30 degrees, and because it's positive, that would be a first and second quadrant solution. Therefore, x is equal to 30 degrees plus 360 degrees times k, or x is equal to 180 degrees minus 30 degrees plus 360 degrees k, again acknowledging the period over which the solution is valid. So that simplifies to 150 degrees plus 360 degrees times k, again where k is a member of the integer family. I think that's good enough. So obviously, for our equation simplifications, there are some marks, reference angles, and then for the actual solutions as they sit. Moving right along, we have a diagram where we have coordinates for P, minus 3 and 17, some point Q, and another point S. So Q and S both in the coordinate plane, and then O is obviously our origin. Q and S are vertices. The sides OS and OQ are defined by the following equations. Y is equal to 6x and y is equal to negative x respectively. Angle QoS is equal to alpha. That's what they say. So determine the equation of QP in the form y is equal to mx plus c. Well, if we have a look at the information we were supposed to transpose, damn mistake, should have been okay. So OS is 6x. Let's get that properly transposed over here. So that has y is equal to 6x, and that's y is equal to negative x. Rightio, now we have more information on our diagram. So determine the equation of QP. So that's QP. Now there was an important word over there in our problem statement. Parallelogram. Parallelogram. What does that mean? Well, it means these lines are parallel as these lines are in the other direction. So the gradient of QP is equal to the gradient of OS. Why? Because QP is parallel to OS. So the gradient of QP is just equal to 6. And of course I have a point over here, so I'll just use y is equal to mx plus c and then sub in the gradient of QP and P, which has coordinates minus 3 and 17. So 17 will be equal to 6 times minus 3 plus c. Therefore the value of c is equal to, well, that's minus 18. 18 transposed will give 17 plus 18, which is thus 35. Therefore y is equal to 6x plus 35. Hence determine the coordinates of Q. Well, in that case, OQ over here, which is defined by minus x, is going to be equal to our new equations over there. So we'll have 6x, so this is for B. Let me just delineate it. 6x plus 35. Or maybe use another color. Yeah, let's get it to stand out. It's getting a bit crowded in this space over here. 3. So I'm going to say 6x plus 35 is equal to negative x, just using this equation and the one we determined here, which is valid for that line, which means add x on both sides. That zeroes out, that's x. So we have 7x being equal to, of course, negative 35, because I'm going to transpose that value to the other side. So x is minus 35 divided by 7, which gives us minus 5. And if we substitute that into the easiest equation, minus 5 just gives us a positive 5. So y is equal to 5. Therefore, the coordinates of Q are going to be minus 5 on the x value and 5 on the y value. It's cute. I think I was way too generous with the mark allocation. 3 marks is more than good. 1 for setting up the equation, 1 for simplification, and 1 for our coordinates. Although, for the y value, you might get the other one too. And then over here, well, that might have been stingy again. It's 1 for the gradient, 1 for substitution, and 1 for answering the actual question. No, I was not stingy. How did I hear myself explaining it? I was actually accurately generous. So, calculate the length of OQ, leaving your answer in simplified search form. Well, the question over here is, do you remember the distance formula, because properly applied and substituting the values in, you'll just get 0 minus minus 5 all squared plus 0 minus 5 all squared. Well, assuming the square root of 25 plus 25, which is equal to the square root of 50, which I can rewrite as the square root of 25 times 2. Square root of 25 is just 5, and the square root of 2 remains square root of 2, and that is the simplified third form. Radio, I'm gonna need to, as they say, just clean out this. Boom. Unselect. Come technology, walk with me. There, got a pen back. Now they want size of alpha. Well, that's y is equal to negative x. Okay, so the gradient of OQ is equal to negative 1. You can read it from there. For if we give that angle of inclination the name beta, we can say that tan of beta is equal to negative 1. Therefore beta is equal to inverse tan applied to negative 1, and then we'll add our 180 degrees because we don't want that angle over there. That's not the one we want. And then we'll get 135 degrees. Well, we do know that gradient over there for OS, gradient of OS again is equal to 6, and then we can call this, well, they haven't used theta, so we'll use it. We'll say therefore theta is equal to inverse of tan applied to the value 6, which gives us a value of 80.557 degrees. And as we can see over here, if we use another color, alpha is just equal to beta minus theta, so we'll state as much. That's just in the way we set it up, and if we take that value and subtract 80.557 to one decimal place, we will get 54.5 degrees. So that's as simple as that gets. And then the final question in our assignment tells us that if OS is equal to that length over here, calculate the length of QS, which is this one. This is the length they want over here. So we have coordinates over there, which is -5 and 5, and then we also have the distance over here, so we know that is 5 times the square root 2. We also have that length of OS, which they have just given us as the square root of 148. We also have this angle that they asked us to calculate, and that ended up being 54.5. Now if we can have a look at this, now even though it's coordinate geometry, it does stop them from integrating it with some other topic, in this case some two-dimensional trigonometry. And what am I referring to? The cosine rule. No? So basic version states that a squared is equal to b squared plus c squared minus 2bc cosine of a. So there we have two sides and an included angle. So let's get going, because what we'll have is that, well, QS is what they want, sitting right in the correct place. So it's going to be QS squared being equal to OQ squared plus OS squared minus 2 times OQ times OS times the cosine of, well, alpha. Now it's just a question of substituting. So QS will be equal to the square root of, well, 5 times the square root of 2 all squared plus the square root of 148, again all squared, minus 2 times 5 times the square root of 2 times the square root of 148 times cosine of 54,5 degrees. Make sure to complete that radical, and if done correctly, should end up with 9,9. And that, ladies and gentlemen, is the end of that. Hopefully next time I'll be more fun and jokey, and hopefully your winter is warm, because this is promising to be cold. Next time.